Hello, so here are my crystals at the point of Alum video 3. As you can see, they now occupy the whole base of the structure of the little beaker. So that is about a 1/3 increase in area compared to last week's. It should be noted that the solution volume has decreased, and that is because as the solution evaporates, we see more crystal growth. So it's natural that the solution level would be lower as the number of crystals increases. I will talk about now if there have been any changes in environmental factors that may have affected our crystals. And one factor I can think of is that my roommate likes to keep the window open, and so the temperature in our room is also dependent upon the temperature outside. And as the days have been getting warmer, there has been uh, a little bit more heat in our room. And as we know, the reaction is spontaneous, therefore, it is also exothermic, which means heat is a product of the reaction. And so, if we were to add more heat, which in this case is being brought in through temperature convection, this heat is a product, and it's going to therefore shift the reaction more towards the reactants, and our crystal rate will slow. So, as we know, this beaker is pretty much just a solution moving towards equilibrium at a very, very slow rate. And what that means is that as the reactants, which is the solution, decrease, there will be more product, which is the crystals, what we're seeing. I conducted some research as to how to create one large crystal, and one solution that I found, which was interesting, was using what's called a seed crystal. So essentially, we would do everything we did, get our solution to be saturated, and then we would add a small crystal to the solution. And what this would be is it's called a seed crystal because in a way it's like a planting ground for where you want to grow your large crystals. And because the solution would be saturated, the crystals would begin to grow around that big one, and it would just continue forming a larger and larger single crystal. Now I will explain the scientific significance of despacing. So, in a crystalline structure, the way atoms are rearranged is in such a way that they create different repeating but parallel planes. So that means that this plane here is parallel to this plane here, which is parallel to this plane, and this one, and so on. Now, despacing is the space between two planes in a crystalline structure. And the scientific significance of this is that because each crystalline structure has its own inherent properties, we can use d-space and X-ray diffraction in order to figure out what kind of crystalline structure it is. Additionally, d-space tells us about density, and this can be thought about in an intuitive sense. If the atoms are closer together, then it's a more dense, tightly packed crystal, whereas if they're more far apart, it is a less dense crystal. Now I'm going to talk about how to use the X-ray powder data on canvas to calculate the d-spacing for the most intense peak in the diffraction pattern. So first of all, the reason why we use X-ray diffraction is because they deflect off parallel planes that are the ones created by the d-spacing. And so there's this formula called Bragg's formula, which is written out right here. And using the XRD data provided to us on canvas and the equation, we can use that to figure out the d-spacing. So we'll notice here that this is the equation, and we want to find the d variable. We know theta because it is 21, but since it's in terms of 2 theta, we must divide by 2 in order to get 10.5 degrees for our theta now. And we know n is 1 as well, And we know this lambda value is 0.15418 nanometers, and that was provided to us on Canvas. So then simply all we have to do is plug all of our known variables into our equation. This is times 1, so it just itself. And then we want to isolate D, and then through just algebraic manipulation, we come out to D equals 0.423 nanometers. And what that tells us is that the D spacing for alum crystals is 0.423 nanometers.